The next thing that I want to talk about is called improper integrals. Before we begin, I want to show you why this can be a problem. Because of the squaring, 1 over x squared is never negative. So if I start at some number, say x equal -2, and I travel to the right, say x equal 1, the integral from -2 to 1 over x squared dx, is the area under the curve, and areas are not negative. If I do as we would have done in the first semester, find an antiderivative, evaluate it at the upper limit of integration and the lower one, and then subtract, I find out that this quantity, which most certainly can't be negative, is -1.5. Obviously, something is wrong here. If you look back in the first semester, when you were talking about this, I believe in chapter 4, the statement that you had was if f is a continuous function on the interval that starts at a and ends at b, and g is an antiderivative of f, that is to say, g prime is f, then you can evaluate this integral by evaluating g at the upper limit and lower limit of integration and then subtracting. The thing is, there are strings attached to this. On the one hand, I have to be able to find an antiderivative, which in our examples, no problem, but the thing that I'm integrating must be continuous on this closed interval of numbers a to b, and this is the source of the problem in our example. 1 over x squared is positive, regardless of the x, assuming, of course, it even makes any sense. But the problem is that at x equals 0, 1 over x squared is undefined. The graph has a vertical asymptote there. I can't draw the entire graph starting at -2 and ending at x equal 1 without picking my pen up. This function is not continuous on the interval from -2 to 1. It is not continuous on any interval of x numbers that contains x equals 0. Therefore, the statement about if f is continuous and you can find an antiderivative is irrelevant. It doesn't apply. The way that people usually deal with this is, let's suppose we have an interval of numbers, a to b, and f acts badly at one spot. X equals 0 in the previous example. We will split the interval up into chunks separated by the bad spot, or bad spots in case we have more than one of them. I still can't do the antiderivative thing because f acts badly at gamma. The idea is I'm going to sit at the bad spot and in this first chunk back up a little bit until I'm at some particular number L. Then the integral from a to L f of x dx makes sense then, although I am omitting some numbers between L and gamma. In the other chunk, I'll pick a number r that's bigger than gamma, and I'll integrate from r to b instead of gamma to b. Again, I am omitting some numbers between gamma and r, so I need to do something about that. Staying to the left of gamma, I'm going to let the L increase and approach gamma, never actually equaling it, though. I'm going to look at the limit of the integral from a to L as L approaches the gamma from the left side. Likewise, I'll look at the integral from r to b f of x dx and allow the r to approach L from the right side. In this way, taking the limit, the only number that gets omitted from consideration is x equals gamma. If both of these integrals exist, meaning actual real numbers, then I add them together, and I'll call that the integral from a to b of f of x dx. If either one of or both of these two limits doesn't exist, then we say that the integral doesn't exist. In either case, we call this an improper integral because the thing that we're integrating isn't continuous. Of course, it doesn't matter what letters I call things. I'll call them whatever's convenient for me. Returning to our problem, I want to integrate from -2 to 1 over x squared dx. I will integrate from -2 to some negative number b that's close to 0. And then I'll take the limit as b approaches 0 from this side. I will integrate from a to 1, where a is some positive number close to 0, and then I'll take the limit as a approaches 0 from the other side. In the limit, the only number that gets excluded is x equals 0. If both of these limits of integrals converge to actual real numbers, then we'll say that that's the value of the integral. If even one of them doesn't, then we say that the improper integral doesn't converge, doesn't exist, diverges, language like that. After doing the algebra and simplifying it a little, I find out that I have to look at the limit as a tends to 0 from the positive side of 1 over a minus 1. The 1 doesn't depend on a at all, so convergence or divergence, this limit doesn't depend on that 1. A is always going to be positive, so 1 over a will be positive. As a gets close to 0, 1 over a then will become a big positive number, and by making the a close enough to 0, I can make 1 over a as large as I'd care to make it. This limit doesn't exist. It does not give you numbers that seem to be settling down to some particular real number. When we write that this equals infinity, that's slightly cringeworthy. There is no actual number named infinity, and this limit, when we write it in this form, makes it look like there is. What we mean by this is these numbers, 1 over a minus 1, do not converge to anything. They can be made as big as you want to make them, and we just symbolize it by saying equals infinity. We really should say this limit diverges, or even diverges to infinity would be a better way of saying it than equals infinity. But this is standard language, so we're stuck with it. Doing a similar argument for the other part, I find out that I need to look at the limit as b tends to 0 from the negative side of -1 over b minus 1/2. The minus 1/2 is a constant term, so that doesn't concern us any. As b approaches 0 from the negative side, 1 over b will be a negative number with large absolute value. The negative of such a number is a positive number with large absolute value. So just like with the other one, this limit doesn't exist. It diverges by becoming indefinitely large in value, or to abuse the language in the standard way, equals infinity. neither one of the two integrals involved converge to an actual real number, that is. So we will say that the integral from -2 to 1 over x squared dx diverges or fails to converge or doesn't exist. Now, you might think that if the function you're integrating has a bad spot on it, then that automatically means that the integral isn't going to exist. This is untrue, as we're going to see with this example. Integral from -1 to 8, 1 over cube root of x dx. 1 over cube root of x is undefined at x equals 0, so we're going to have a vertical asymptote there. But as we're going to see, the integral is perfectly well behaved, and actually, sort of bizarrely, if you didn't notice that there was a problem with the integrand, the 1 over cube root of x, and just blindly followed the antiderivative procedure, you would actually get the right answer, even though, because of the bad behavior of the function, that theorem isn't guaranteed to work here, but in fact it does. The cube root of x is x to the 1/3 power. 1 over cube root of x is x to the -1/3 power. I can reuse the antiderivative that I use for one of these in the other, although the limits will be different. Since we're integrating a constant power of x, and the power is not -1, we can use our familiar trick involving the integral of x to the n power. An antiderivative is 3/2 x to the 2/3 power, which I can write in a little bit nicer way as follows. My antiderivative is 3/2 multiplied by the square of the cube root of x. Now, I'll evaluate my integrals and take the appropriate limits. As a approaches 0, the cube root of a also approaches 0. The square of a number that approaches 0 approaches 0. So the limit of this second term is 0. The cube root of 8 is 2. So I have 2 squared, which is 4, multiplied by 3/2, which is 6. The integral that corresponds to the right part of the situation, the rightmost part, converges to 6. The cube root of -1 is -1. When you square that, you get 1, so we are subtracting 3/2 here. On the other hand, when b is small and negative, cube root of b will be as well. The square of a number of small absolute value is small. The limit of this first piece, as b tends to 0 from the negative side, is 0. So this limit converges as well and is equal to -3/2. As a result, the value of the integral is 9/2. The integral converges to 4.5, if you'd like to put it that way. As I mentioned previously, if you just find an antiderivative of 1 over cube root of x, evaluate at 8 and -1 and subtract, you end up getting the correct answer, but that's not always guaranteed to happen, as we saw with the first example we looked at. We'll call these improper integrals of the first type. We start at some specific x value, we end at some other one. The problem is that the function has some sort of bad behavior in the interval upon which we're integrating it. We're also going to have improper integrals of the second type, but I'll talk about that in the next video. In the meantime, I hope that everyone's having a good day. I'll talk to you again soon.